Welcome everyone to today's session. So today's session is titled Introduction to Causality for Machine Learners. We'll talk about causality broadly, not only about causal discovery that Jean mentioned before. We'll also talk about causality in general a little bit, because we will need this background in order to make the best out of this session. I want to start with traditional machine learning, though. So we can imagine the following business idea. We have a housing market, or real estate market. And then maybe we think, okay, I'm good at machine learning. Maybe I could collect some features about houses and about the market and build an ML model that would allow me to predict a price for a given house, let's say a market price. And then if I see that the actual price is below the price that I predicted, I could buy this house and flip it soon with profit. It turns out that somebody thought about this idea, and that was a company called Zillow. This company was pretty successful with their house flipping business, although that was not their primary business. And suddenly, at some point, they completely crashed with this house flipping business. So there were many articles about this. There was winter 2021, like fall and winter. You can see here Zillow touched $381 million. Then Zillow reports $880 million loss on failed home flipping business. And so people were thinking about this case and proposed many different reasons why this happened. But there's one particular reason that I think is, or at least can be thought of as the main underlying cause of the failure of this idea. And this is related to distributions. So this idea with decisions to buy or not buy can work, but it can only work if and only if the distributions in our feature set are stable. What does it mean? This means that we train the model on certain distribution of features regarding the houses themselves and the market. And then at the prediction time, we assume that the distribution is also stable. It hasn't changed. But this is problematic, because in the real world, we face dynamical systems that are changing. And so if we think about distributions that are completely stable over time, this is like taking a snapshot of reality. And this snapshot might be a good approximation of reality for a certain amount of time, but then it becomes outdated at some point, very often. And so in machine learning, we map features or the data to some output or some target based on statistical properties of the data, right? So we try to find patterns in the data and say, okay, if there is this pattern, then the output is likely this. If there's another pattern, the output is likely something else. And this is really great for prediction, but under the IID assumption. So IID assumption is the assumption of identically and independently distributed random variables. And as Bernard Schulkopf called this in one of his recent presentations, this is the biggest lie of machine learning, the IID assumption. Well, technically, of course, it's not a lie. It's just an assumption, but we sometimes forget about this assumption. And when we forget about this assumption, it's very easy to put ourselves or our projects at risk similar to the ones that Zillow faced in their journey. If you want to learn more about this idea, you can see our conversation with Bernard in Causal Bandits podcast. This is available on YouTube and also on all major podcast platforms, so you can listen or watch. Okay, going back. So this is great for prediction under the assumption, but this idea of machine learning or traditional supervised machine learning or semi-supervised or self-supervised machine learning fails under the violation of the IID assumption. Why is that interesting? Well, I argue that most of the most interesting questions in business and science are questions about how the world will change if we change something. Let me give you an example. For instance, if we run any type of business, marketing is important to us. And we often want to understand what is the optimal decision, or which decision would be better in our marketing than something that we are doing today. So perhaps, should we change our marketing mix? Should we start, or should we continue, or should we increase the budget for our Facebook ads or Instagram ads? Should we place billboards in Los Angeles, for instance? So all those questions are causal, because these questions are not about the prediction regarding the world, how it is. These are questions about, what if we do something? What will change in the world? What will be the response? So there is this dynamical component to this. And these questions are questions about interventions and their effects. So interventions, we call interventions. By interventions, we mean any type of change or action that we take in the world, that we carry out in the world. Another way to express it is that observations are an incomplete and static snapshot of a dynamic system that we want to model. And this is important to understand that what we currently have in machine learning is based on statistical patterns. We mentioned these patterns a while ago when we were talking about the mapping from features to the outputs. And as it turns out, statistical patterns do not contain enough information to allow us to understand the structure of the data generating process behind the data that we observe. What does it mean? That means that we have a certain process. We are observing some outputs of this process, and we can show mathematically from a number of perspectives, measure theoretic perspective, topological perspective, and more, that based on our observations themselves, we cannot recreate the data generating process. And now, when we are interested in modeling our actions in the world, not only predicting the state of the world, assuming that the world is static in terms of the underlying distributions, if we want to model our actions, we need to understand at least something about the data generating process. In other words, if I want to predict what will be the outcome of me throwing this pen in this direction, I need to capture somehow the notion of my intervention, of me throwing the pen. But data is not enough. Why exactly and how to overcome this, we'll see in a second. And before this, I want to quickly introduce myself, because I started talking about machine learning in the beginning. So for those of you who don't know me, my name is Alex. I'm a consultant and educator. I'm the author of this book called Causal Inference and Discovery in Python. You can learn more about the book here if you scan the QR code. I'm also a tutor in causal machine learning at the University of Oxford and host of the Causal Bandits podcast. And we just recently released the last guest episode of the first season of this podcast with Professor Judea Pearl. If you heard something about modern causality, you probably heard his name. He's the author of The Book of Why and a number of other books. The godfather of causal AI. I think that's very fair to say. You can see this episode here if you scan this QR code. And now we go back. So we said that data is not enough to model our interventions. And we talked about this dynamical nature of the reality that we cannot capture under the IID assumption, at least as long as we do not sample at random from reality, from everything, all scenarios, which I think, as of today at least, is impossible. So these ideas are crucial, but what do they have in common with causality? What do they have to do with causality? So I want to ask you a question. How to increase the number of non-commercial space launches per year? And I don't want you to answer this question. I will answer this for you using data. And then I will ask you a question, and I would like to hear your answer, what you think about this answer. So one data-driven answer is to increase the number of PhDs in sociology in the US. And the data that shows that this answer, at least in certain, in terms of certain criteria, is plausible, is this data. So you can see that there's a correlation between the number of sociology doctorates awarded in the United States and worldwide non-commercial space launches. And this correlation is pretty strong, and it holds consistently for over a decade, from 1997 to 2009. So is this a good candidate for a causal explanation? That's my question to you. And I'd love to see.
You want us to check the chat maybe for you? Let me just check if we have some.
Oh, if you could, that would be great. Because
I'm checking if there's some answer. So Marcio is saying no.
No.
With a very strong no. Royston is going, I don't think it's related.
Okay. Why do you think it is not a good candidate for causal explanation, for a causal explanation?
Let's check. So Satish saying answer is no.
No way. The answer is no.
Now your question is why? Why is it not a good candidate? So we expect something different from just no.
Coincidence. Royston says it's a coincidence. Okay, it might be a coincidence, but why is it? Well, given what we've seen here, why do we think this is not a good answer? It might be a coincidence, and that's fine. But we look at the data, and now, what makes us think that all of this correlation is strong? Mm-hmm.
I like this answer. They are not related from Satish.
They are not related. How do we know they are not related? Satish, or maybe someone else in the chat. How do we know, or why do we think they are not related?
So Bjorn is saying, again, we only see a statistical correlation between two output patterns.
Mm-hmm. Yes, that is correct. That is correct. But sometimes here we understand what those variables means, right? But sometimes we go to the world and we observe something and we only see the correlations. We don't maybe even know what's the meaning of variables.
We have two people that are raising hands. So I'm going to open the mic to Jeremy.
Please do. Please do. Yes, let's hear from them.
Jeremy, how you doing? You can talk now. You just have to unmute your mic.
Hey guys.
How you doing?
Hi, Jeremy.
Hey, Jeremy.
Yeah, sorry about that. I didn't mean to unmute, but that's okay, I guess. Yeah, the correlation is not causation. We know that. I mean, that's the topic of the day, I guess. But yeah, I mean, having something awarded correlating with basically a fact that's launching non-commercial rockets, to me, is not a straight and even indirect link between the two of them. I mean, a paper and a discovery is obviously difficult to correlate together, in my opinion. So, yeah.
Thanks,
Great.
Jeremy.
Thank you. Thank you for sharing, Jeremy. I see we also have some more answers here in the chat. And so I just will try to briefly summarize them. So one of the answers that I think was really nice here is from Javier. And Javier says, our model of the world tells us they should not influence each other. And then we have a couple of other answers that are suggesting that there might be a third variable that is impacting both of those variables. And then we will see a correlation, of course, but they don't have to be causally related themselves. So they can be correlated through a causal impact of another variable. That's a great idea. And then we have another answer here from Björn. Usually we have rival causal theoretic explanations in our head, which we test or falsify using the empirical observations. Mm-hmm. That's a great idea again. And then we have from Andreas and Vikrant about confounding and about independent events. Yes, great.
And Alexander, is it fair to say that they are not listening to each other? So
this is something you you went ahead a little bit of the presentation, but that's a great intuition, Jean. So yes, thank you for sharing. Definitely. So so most of us, at least, or probably all of us, agree that they are not a good candidate, that this is not a good candidate for a causal explanation. The number of sociology doctorates is not a good candidate for a causal explanation of the number of non-commercial space launches, even though they are very strongly and consistently correlated. And if we look at something like Bradford-Hill criteria, we'll see that strong correlation according to those criteria and a correlation that is consistent. We are recommended to treat this as indications of potential causal explanation. But we see here that those two criteria are definitely not enough to make sure that there's a causal relationship between two variables, even if those two criteria are met. Midterm kind of takeaway is that causal knowledge goes beyond the data itself. And I think that has been captured here in one of the comments about causal models that we already have in our head, or causal theoretic explanations, as Bjorn called it, that we are trying to put those variables into the context and try to reason about them. So we don't only look at the data, but we are also trying to put some structure to the data and think, oh, would that be plausible that they are connected causally? Would that be plausible given all we know about the world today? And so I want us to remember this takeaway, because we'll get back to it in a couple of slides, maybe more, maybe 10 slides. But this idea will be important for us, that causal knowledge goes beyond the data itself and the statistical patterns in the data. But what is causality? So here's a definition from Wikipedia. Causality is the relationship between causes and effects. And this comes from Wikipedia, from an article that talks about causality in physics. And our time is limited, so I will skip the questions, but I usually ask the audience if the audience thinks that this is a good definition. And some people think it's a good definition. Some people think it's not very good. I think it's not very good because it defines causality using causes, which is possibly a circular, makes it a circular definition. But it's also not necessarily very useful, because it doesn't tell us anything about causes and effects. It just says like, okay, this is some kind of a relationship between causes and effects. It does not specify the direction of this relationship. It doesn't tell us anything about those more basic entities here. So we have more definitions of causality, and we had many historically. Plato, for instance, said that causation is not physical but metaphysical, which, if you think about Plato's ideas, might make sense. Then David Hume said that due to their constant conjunction, we are psychologically certain that B will follow A. We need to be fair here, and we need to say that that's only one definitional criterion for causality that we can find in Hume's writings. There's another one that is more counterfactual, I would say. But this one is psychological. So it says that basically, if we have two different events and they are repeatedly, one is repeatedly following the other, we are getting used to this, and then we start thinking that they are causally related. That's problematic, of course, because, as we said, a statistical pattern is not enough for us to determine a causal relationship between variables. So if we can imagine a person that was living for these 12 years from 1997 to 2009 and was observing space launches and PhD, now the number of PhD doctorates, according to this definition, and this relationship should have been treated as a causal relationship by this person. So that's a very brief and very selective trip through the Western philosophy. We have definitions of causation as well in the East, and they are different, and that's very interesting how they differ from Western definitions. But all the definitions that we've seen so far are not very useful. They do not seem very practical. Can we do something about it? So there's one definition that I would like to propose for us for today, and it comes from Judea Pearl, and it refers to the idea that Jean shared with us a while ago. And the definition says, A is a cause of B if B listens to A. So that's a little bit metaphorical, maybe. So let's unpack it. Listens to here means that if we change something in B, we also expect that if we change something in A, because B listens to A, we expect that something in B will also change. Now, we can think about some special cases here and so on, but for the sake of today's presentation, we will just keep this definition as it is. And an important aspect of this definition is that it is an interventional definition of causality, because listening to means a response to a change. So we need to act, or something in the world needs to act, needs to change, and then we observe a change in another variable. And those changes, we will refer to those changes as interventions. So interventions are important for causality, especially in the Pearlian framework. That's not the only framework that we have on the market. Some of you, I've seen somebody talking about econometrics here, or economics. So many people in economics will be familiar with so-called Rubin causal model, or the potential outcomes framework, which has also been expanded and extended by one of the creators of the causal discovery challenge, Guido Imbens. But we will focus on the Pearlian view here, and I think for a good reason. So interventions are important in this framework. As a margin note, the potential outcomes framework is largely logically equivalent to Pearlian framework, so we can talk about the same stuff, just using slightly different language. But interventions are not the only thing in the Pearlian framework. And to talk about this in a way that is structured, we will use this idea of the ladder of causation. The ladder of causation it's not a one thing, it's many things. But one thing it's a great device to talk about different levels of relationships between variables in a way that is structured. But it is also it comes also with a mathematical framework, or a set of languages, different formal languages that describe those different ranks in this ladder. But let's do not go ahead of ourselves. So what is the ladder of causation? The ladder of causation is this device that has 3 different ranks, and each of the ranks describes a different level of relationship between variables. Associations are like correlation, but also when we think about correlation, it's good to define the term. We are not only thinking about linear correlations, we are also thinking about any other types of association. So if we have a measure theoretic metric, for instance, like, something based on mutual information and so on, all of these things will be associations because they are based on the pattern in the data. They only look at the data and they say, okay, there is some pattern in this data. Then the second rank is the interventional rank. So this rank introduces the notion of acting in the world, doing something. Then the final rank is the counterfactual rank. The counterfactual rank is about minimal changes in the system. I'll give you a more concrete example here. So, for instance, we might imagine a situation where some of us, maybe Max, has a headache today, and Max takes some painkiller at, let's say, 1 hour. He had a headache and took a painkiller.
You're spying me, Alexander.
I hope you didn't have a headache, but if you had, I hope you don't have or won't have it soon. Anyway, so let's imagine that 1 hour ago, Max had a headache and he took a painkiller. Now, he doesn't have a headache anymore. But now, this doesn't mean that the painkiller was the cause that his headache disappeared, right? Maybe his headache disappeared just naturally, and the painkiller did not really affect it. So we could ask a counterfactual question, and this question would be, if Max had not taken the painkiller, would he have experienced headache right now? Right, so that's a counterfactual question. We often think about counterfactuals in terms of the past, looking into the past and saying, "Oh, if we changed something back then, what would be the reality now?" But counterfactuals are not limited to the past. We can also think about counterfactuals in the future. So we say, "Oh, that will be some future state of the system. If we will change something in the system, what will be the state of the system at time t plus some I, t plus I." So counterfactuals, we can also think about counterfactuals as a ingredient of interventions in a sense. So interventional distributions. But I don't want to make it too complicated. So before we move forward, I also want to give you another perspective on the ladder of causation. Associations are related to the action of observing. Interventions are related to taking actions, interventions, intervening in the world, acting in the world. Counterfactuals are related to the action of imagining. So that would be, if we think about counterfactuals, that would be thinking about scientific theories, for instance, building structural causal models, building a theoretical representation of some notion. So I hope this sounds clear, but I want to stop here for just a second and ask if you have any questions regarding this, because these concepts will be important for us. So if anything was not clear, I'll be very happy to clarify this for you now.
Yeah, let's check the chat. I think it's quite interesting. I even see Royston saying that he's now interested in a ML master degree, thanks to you. So yeah, it's top quality, Alexander. Yeah, definitely. Thanks for bringing all of those concepts to our community. I'm checking the chat. I don't think anyone has a question. It seems like very clear and all clear for everyone. So maybe we can move forward. Oh, no, that's the question. What makes an imaginary theory one that we, I guess, do not yet know is true, quote unquote, counterfactual? I'm not sure that I understand the question, but maybe, Alexander, you got it?
What makes an imaginary theory one that we, I guess, do not yet know is true? Okay. So counterfactuals, we won't have time to go into the math behind counterfactuals, but this is a very well-defined concept mathematically. So it's less about the theory being imaginary. It's more about the idea of computing different outputs from a system, given that we change just one thing or maybe a couple of things, but let's stick to one thing, just one small thing. So you can think about this in terms of, for instance, maybe you have a degree, I don't know, you have a degree in economics, right? And you are somewhere in your life. And now you are wondering what my life would be if I did computer science instead of economics, right? So that would be a counterfactual question. But we want to keep everything else constant in this counterfactual world, this imaginary world. So, like your girlfriend or boyfriend, they would be the same, right? And your relationship with your parents and so on and so on. We only change this one thing, your degree. And we see how this propagates in the system which is your life here in this case, how it propagates and what outputs it leads us. And now you could you could say like, oh, okay, that might be difficult because we would need to capture a lot of detail, record a lot of variables in order to say anything meaningful about this, and that would be a very valid concern. So counterfactual inference might be very difficult sometimes, precisely because of this challenge. But still, even though challenging, this is still not impossible. And moreover, in certain cases, we can use observational data and interventional data, combine it together, and get some bounds on counterfactuals. So say like, okay, probability of, if you change your degree, the probability of you having more money today, let's say, would be between 20 and 40%. So we can get a bound like this. I hope this clarifies. If not, please feel free to write another question in the chat.
Yeah, so there's another question actually, but I don't know if it's exactly related to what you're saying or if we should keep it for the Q&A session.
Okay.
So it's a question from Kemal, and it's you said causal knowledge goes beyond data. What other factors affect causal knowledge? Maybe previous theories about worlds?
Oh, great. That's a great question. I think we will leave it for the end because I hope that at least some of the things that we will discuss will give you a little bit more background and will put all of us in a better position to discuss this. Max, if you could remember this question for us,
sure.
So we can.
Yeah, definitely.
Yeah, and then I see we have some more questions. So let's get back to those questions. Some very good questions, but let's get back to them later because I believe that what we'll talk about now will give us a better foundation, to discuss these ideas.
Makes sense.
Great. So we talked about the theory of causality, and I see that it's not entirely clear for all of us so far. Some details here, for instance, how interventions and counterfactuals are different, and we'll talk about this a little bit more soon. But now I want to change the perspective a little bit for us and go into something more practical. How do we translate these ideas into something more viable? So in the Perlian framework, the original Perlian framework, we use this formalism of directed acyclic graphs, or DAGs. For those of you who might say like, oh, but some systems are cyclic, well, maybe we can argue at the end of the talk if that's really the case. But even if we cannot be sure, or our data, the frequency of sampling of our data does not allow us to unroll a system into the acyclic form, there are other formalisms that can be applied then. One of them comes from Bernard Schulkopf that we mentioned earlier, and his collaborators Lars Lorch and Andreas Krause. And they proposed a method that uses stationary diffusions and stochastic differential equations in order to capture causality in systems that are modeled as cyclic systems. But we will focus on DAGs today, and there are good reasons for this, because it will give us much more clarity in order to build, and we'll be able to build on top of this in a much more efficient way, effective way, than if we go into the details of other alternative approaches. So let's imagine that we have a fire alarm system, and this fire alarm system only consists of 3 elements or 3 variables. The alarm itself only reacts to smoke. Okay, so this is a smoke detector-based fire alarm, which means it won't react to the temperature. It only reacts to the smoke particles in the air. And so, if we think about this, we could present it as a graph like this. There is a fire. Fire causes smoke, and smoke causes alarm. We can think about this probabilistically or deterministically. For the sake of simplicity, we can think about it now deterministically. But there's nothing in this entire concept, entire framework that we are discussing that would not allow us to think probabilistically. It's actually a framework that comes from probability. So, okay, so we can think about this way. Now, there is an interesting property to the system. And the property is that if we control for smoke, which means if we observe smoke, alarm and fire become independent. In other words, giving you a practical example, if I came to your room with a bag full of smoke and I would just release the smoke, the alarm would go off. If there was a fire in the room, but we open the window and make sure that all the smoke goes out through the window, the alarm would not go off. Which means that smoke, all the information that comes from fire to alarm goes through smoke. And if we observe smoke, there is no additional information in fire from the point of view of the alarm. Now, an interesting thing about this is that this example, we can make this example more abstract. Just say there are some three variables A, B, and C, and the same independence pattern will hold, which means that whatever variable is A, if A causes B and B causes C, and we observe B, A and C become independent. In other words, this is also called the conditional independence, which means that A and C are conditionally independent given B. Unconditionally, if we don't control for B, we don't observe B, A and C will be related because there is some information flowing from A to C via B. But if we control for B, you can think of it as closing the water flow in this line, in the direction of the arrows, and A and C become independent. So it turns out that people are thinking about this for a while, Judea Pearl and other people as well, and this already has a name, and the name is chain. So this structure is called a chain. But that's definitely not the only structure that we could construct between three different variables. And there's another structure called a fork. In fork, we have B causing A and B causing C. Now, I will ask you a question. If we just observe the system as it is without controlling for anything, will A and C be dependent or independent?
Interesting. Waiting for your questions in the chat, or your answers, probably more than questions. Let's see.
The question is, if we observe A and C only.
So we have Marcio saying dependent and Devendra saying independent.
So Mars is
also someone is raising their hand. Let me just check the chat.
And Björn is saying dependent.
Rahim, you are now allowed to talk. And you should unmute your mic.
Yeah. Good afternoon. Thank you for this session. So if we are trying to consider for A and C without taking B into consideration, A and C will be dependent to one another because we don't have any variable that will make them to be independent. So it will create a spurious correlations between A and C.
Yeah, that's a great answer, and that's also what many people said in the chat. But probably most people said this in the chat. So if we only look at A and C, they will be dependent. And that will be one of the potential models that could explain the data that we've seen in the space launches versus sociology PhDs, right? Maybe there is a third variable that is impacting both the number of non-commercial space launches and sociology PhDs. So maybe the doctorates would be, or the PhDs would be C, and then space launches would be A, and B would maybe be, I don't know, economy or whatever this is. But if we control for B, as Rahim told us, if we control for B, they will become independent because there is no other information flow between those two different variables other than through B. So they are inheriting some information from B, both of them. But if we control for the source of information, there is no other source of information that they share. That's great. So we had a chain and now we had a fork, and we said, okay, the independence, the conditional independence structure between those two are identical, which again goes back to our conclusions, to our takeaway. The data is not enough for us. The data itself is not sufficient for us to recover the structure of the data generating process, right? Because if we look at these conditional independencies, well, it's the same set of conditional independencies, but the structure, the causal structure is different. But again, these are not the only two possible structures that we can get for three different variables. There's another one, and it's called the collider. And so here we have, in a sense, a reversed case. So B is being caused by A and C, both of them. So now a question for you will be, if we observe only A and C, will they be dependent or independent?
In the chat, independent. Initially independent, but if we control B, it becomes dependent.
Independent.
Answers are mostly independent.
Yes, and these are good answers. Exactly. So they will be both independent, and if we control for B, they will become dependent. I see like there are very good answers here. Great. So that's correct. It seems to me that this is clear for you, so we won't go into the details or into intuitive explanations for this. We'll jump into the statistical thing now. So now you can see this is here I generated three different data sets where A and B are predictors and C is the dependent variable. And this is to illustrate, to show you that the independent structures here are the same. So if we control for B, A is not a significant predictor of C. And then if we control for B here, A is a significant predictor of C. So we can see that although we cannot distinguish between two different structures here, we can actually distinguish this structure, which is called the collider. And this is some good news for us. Now, if we want to model causal systems, or if we want to build models that can generalize beyond the IID distribution, we need to understand which variables we should control for in the model, or in other words, which features should be selected into the model. Because if we control for a wrong set of variables, our model might perform very well under the IID assumption, but it will fail when there is some violation of the IID assumption. And this is multivariate IID assumption, right? So this is, in a sense, a very strong assumption. If you want to learn more how to do it, you can see this, you can check this paper, A Crash Course in Good and Bad Controls, from Carlos Sinelli, Andrew Forney, and Julia Pearl. That's a very good paper. And also one of the ideas here is that if we control for a set of variables that is not reflecting the causal structure of the system that we are modeling, we can get a statistical model with very good properties, very good statistical properties, that will be very far away from the reality. And there's a great paper by Marcos Lopez de Prado, the second of the designers of the competition, the Causal Discovery competition, where he shows exact criteria how to create a model with excellent statistical properties that will completely fail under the distribution, minor distribution shifts, because it does not mirror, it does not reflect the causal structure. And so in this sense, we don't need an LLM to experience hallucinations from a model. Linear regression is enough. We can build a great linear regression that has excellent statistical properties, small p-values, but it will not reflect the world. Okay, so now to the most important part for those of you who are going to participate in the crunch. Causal discovery. So we said before that causal knowledge goes beyond the data itself. But it turns out that we can learn something about the data generating process from the data itself if we can make some additional assumptions. And this will be our small eye of the needle, where we sometimes can go through to the causal world, even if only think we have our observations. There are four main families of causal discovery methods. In general, causal discovery is the idea that we take some data, either observational or interventional or mixed, interventional and observational, and we use this data in order to recover the causal structure, or in other words, the structure of the data generating process. So which variables cause which variables in our system. And the four families of those methods are constraint-based. Constraint-based are, in other words, methods that are using conditional independence testing. So the ideas that we just discussed about three different structures, forks, colliders, and chains, are used in those methods in order to recover the structure. But because there is an equivalence of the conditional independence between there is an equivalence in conditional independence structure between forks and chains, sometimes the best we can get is so-called Markov equivalence class. Markov equivalence class is a set of graphs of DAGs representing the data generating process, the structure of the data generating process, that all match our data in terms of conditional independencies. If we are lucky, we sometimes can get a DAG. We go down to a DAG, but sometimes we'll just get this Markov equivalence class. Then we have score-based methods. Score-based methods are, you can think of as building a hypothesis regarding the data generating process and seeing how well the data is fitting this hypothesis. So we often use here stuff like Bayesian information criterion or something like this, some data fitting statistics. And here we often use so-called greedy approaches, which means we just go and we cannot search the entire space. We just say, okay, hey, this looks good. Let's move on. This might lead to some challenges, but in certain cases, these methods perform very well. Then we have functional methods that try to find the traces of the data generating process in the data. So we will see an example in a second. But those methods will usually require us to make assumptions regarding either functional forms of the relationships between variables, for instance, that variables are linearly connected, and/or assumptions regarding the distribution of variables. So for instance, the variables are non-Gaussian or they are Gaussian. It depends which method we talk about. And finally, we have gradient-based methods, which in a sense, they could be thought of as a subset of score-based methods, but because they use deep learning kind of solutions for optimization, we talk about them often as a separate category. And finally, we have other types of methods based on reinforcement learning and a whole bunch of different ideas. So I want to share with you two methods a little bit more in depth. So this is a so-called PC algorithm. PC algorithm is an example of a constraint-based method. And here we can see the steps of the PC algorithm. The first figure here, A, represents the actual data generating process. B is how we start with the PC algorithm. We assume a fully connected graph. Then we remove the edges that are unconditionally independent. And then we start looking for so-called colliders. this special structure that has a different conditional independence, leads to a different conditional independence landscape than other structures. We look for colliders and we remove all the edges based on the information that we get from conditional independence tests, but from the identified colliders. Then we use those colliders to identify the direction of the edges, because we know that a collider has a special conditional independence properties that are different from anything else, which allows us to orient the edges. And then here we are actually lucky. And because we know that Z is not a collider between Y and W, we can read this from our conditional independence test. We can say with certainty that the arrow goes from Z to W, not the other way around. So that's the PC algorithm. One challenge of the PC algorithm is that the number of conditional tests required to test a set of variables grows super exponentially with the number of nodes, which means that for 10 variables, the number of independence tests is already huge. And for 5,000 variables, this is not something that is computationally feasible in most cases. But I know industrial cases where people use this, they just put this on very huge fast machines, and this algorithm works for like 3 or 5 or 7 days, and they get their graphs. So if somebody's motivated and they can allow, and their use case allows them to use so much time, and then it can be still feasible. But there are some more challenges with this algorithm. There's so-called faithfulness assumption. We won't have time to discuss it, but the soft violations of faithfulness assumption can happen in reality. And also you can imagine if our sample size is small and the relationship between two variables is pretty complex, it might be very difficult for even an advanced, let's say some mutual information based or like kernel based test. It might be very difficult for this test to actually give you a meaningful result, right? Because if you imagine a very complex, very curvy relationship between two variables, and we have only 5 points, we have no idea if this is just noise or these points are just coming from a very complex relationship. So that's one of the intuitions for some of the challenges behind the PC algorithm. And then we have the functional based methods. Here we see, I said Lingam, but this is actually A&M. So another methods from the same family, additive noise. Oh no, sorry, this is Lingam actually. Yeah, this is Lingam. So you can see that for linear and Gaussian case, if we regress x on y versus y on x, the residual patterns will be the same. There is just noise. We cannot say anything. But if we have linear and non-Gaussian data, I think here I'm not sure, maybe that's uniform probably. You can see that now if we change the direction of regression, which variable we regress on which, there will appear a pattern in the residuals. And this pattern in the residuals will allow us to actually decode which direction is causal for any two variables. But this requires us that for Lingam, that the data is linear and non-Gaussian. Now, there are generalizations of this method as well that we'll discuss very briefly at the end. But this idea is another idea how we can play detectives a little bit and go and try to find the traces of the data generating process in the data itself. I thought I have another one, but I don't have. Okay, so how do we do this in practice in Python? This can be very easy. We can just import a library like this comes from the library called gcastle that I discuss in my book. You just have a class PC, you instantiate the class, you use the method learn, pc.learn on your data set, and this will return the causal matrix, where 1 means there's an edge from node 0 to node 1 to 0, 1, 2, from 0 to 2, and so on, right? So you can decode this is a matrix representation of a graph.
Aleksander, I just shared in the chat an example of the PC algorithm using gcastle, by the way, for the current crunch. If you guys want to check it out.
Great.
It's exactly what Aleksander presents.
Great. That's amazing. Thank you, Jean. And then, okay. And then we see here what we learned using this implementation from gcastle. And for this example that we used in the presentation, you see that the algorithm was able to decode and recover the structure correctly. Now, you will see that for different types of data sets, different algorithms will perform differently. So this table shows the values of SHD, structural Hamming distance, which is one of the metrics to compare two graphs, how far away they are from each other, two directed graphs. And you can see that PC algorithm has the structural Hamming distance of 5 for linear Gaussian and linear exponential data, but for nonlinear quadratic data, it goes to 14. The lower the distance, the better. So 0 is perfect recovery, 5 is, well, so let's say 5 errors, right? And so on. Here, it's important to say also that this version of PC here, the implementation of PC here that we used some pretty simple conditional independence tests. So you can always plug in a different test for your PC algorithm that will be more powerful. And this might help you, especially in more complex cases, right? So a test that can work with highly nonlinear data, we would expect that the result here would be much better, and possibly here as well better. Then GES, you can see, it's not performing very well on this data that was used for this particular test. It's 17, 18, and then 13 on nonlinear quadratic. Then Lingam performs pretty bad on linear Gaussian, and this is expected because it requires data that is linear but non-Gaussian. So the Gaussian distribution makes it impossible for the model to uncover some relationships in the data set. But for linear exponential data, Lingam works very well. And this is often true for Lingam. Lingam is a pretty powerful method if we can meet the assumptions. And then for nonlinear quadratic data, you can see that the performance drops very fast again. Then we have Golem. Golem is one of the gradient-based methods. So there's a deep learning optimization machinery behind the scenes. You can see that for linear Gaussian case and for linear exponential, it works very well. But for nonlinear quadratic, the performance drops. So we can see that there are different models might perform differently on different data sets. And one thing that we can do in case of some algorithms, not all algorithms are designed in this way, but some of them are, and PC is in this group, and some variations of Lingam as well, is to provide the algorithms with expert knowledge. So for instance, maybe we know from somewhere else, from prior experiments, or from the literature or whatever, from our expert knowledge, that certain variables are not connected. Or maybe we know that there are two variables that are connected. And so you can see that the performance goes up significantly for this in this experiment for the PC algorithm when we provide prior knowledge to the algorithm. The recovered graph is much closer to the true graph than in this case, right? And we see that structural Hamming distance goes from 5 to 2, and F1 score from 0.75 to 0.991.
Alex, just don't want to interrupt, but just doing a time check.
Yeah.
Do you still have a bit of time so that we can cover some questions?
Yes, I will be able to stay for probably like 7-8 minutes longer.
Okay, let's do it. So if you can, know when I can start asking you questions, and then we call it a quit. Thank you.
Great. And so when we talk about causal discovery, especially for cases that are safety critical, it's a common practice to use human in the loop. We also have other methods that lead to consistently to much better results if we can allow for interventions or randomization somewhere on the way. And those methods will recover causal structures better than only from observational data. But in the crunch, you have only observations, so you will need to deal with this. Some more ideas beyond what we discussed. This paper, I think from this year, from Shohei Shimizu and Takashi Maeda. Shimizu is one of the original creators of LINGAM algorithm, a very prominent figure in causal discovery, in the causal discovery community. And here they use prior knowledge to discover causal models with unobserved variables. Oh, this is another thing that I didn't mention, right? So for most of these methods, not all of them, but I think all of the methods that we mentioned so far, we assume that there are no unobserved variables, right? So there are no unobserved confounders in particular. This method works on time series data and allows us to uncover the causal structure with unobserved variables. So this relaxes some of the assumptions that we make for many of the causal discovery algorithms. As a side note, if you want a version of PC that works with unobserved variables, you can use FCI, fast causal inference. This might give you not a full DAG always, but it can, at least in some cases, uncover the fact that there is a hidden confounder. So that would be another possibility. And this method is particularly the one that you see on the screen. Is particularly designed to work with the time series data. And you can see that the performance is really pretty good, especially compared with other methods. Here you can see var LINGAM. So this is a variation of the LINGAM algorithm that we've seen before. And with a big enough sample size, approaching 2,000 observations, we can go well beyond 0.9 accuracy in 0.9 recall, a precision around 0.8, which gives us F1 score around 8.85 or something like this. So these are really pretty good results, and that's definitely good enough in many practical use cases. And that's another recent paper from Francesco Locatello's lab with Patrick Bleubaum from Amazon, Elke Kirschbaum also from Amazon, Philipp Faller and Francesco Montagna from University of Genoa. And they use a family of algorithms related to LINGAM. And this family is called score matching. The idea behind this approach is called score matching. And they generalize some of the ideas that we learned about for LINGAM, and they allow these algorithms to work with linear, nonlinear data, and also data where we have hidden confounders. So this is a very, very flexible approach. It's pretty new, and there are many very promising results. All that said, causal discovery and causal inference in general always comes with unknowns. And in a sense, causal modeling causal methodology is the scientific methodology. We really go and discover something new. And this is not always easy. But this doesn't mean that we should not try. And we see many great examples, applied examples of causal modeling in industry that really help companies move forward and build a very strong competitive advantage compared to companies that do not use causal modeling. And before we move to the Q&A, I want to close it with this quote from Yuval Noah Harari. The big revolution which launched modern science was a discovery of ignorance. For thousands of years, people thought they know everything. Science began when some humans admitted we don't know everything. Now, when we have courage to admit our ignorance, we can start investigating. And that's science. Thank you so much.
Wow, so that was well put together. Thank you, Aleksander. That was an amazing presentation. I'm sure that a lot of people from the community are going to like watching it probably several times. Let's jump to the questions. So I have a question from, let me check because I kind of liked it. Yeah, from Akil. How to keep on top of causal machine learning research in these times of everything LLMs?
That's a great question. Causality became a field like 5, 6, 7 years ago. You could probably have a good grasp of everything in the causal modeling niche, but today it's impossible. I just checked. I had this a pitch for one of my talks, I think 2 years ago in Berlin, where I said that in 2022 there were 3.2 papers, new papers on causality released on our archive each day. And I wanted to update this year. I just checked it, and over the last 12 months, it's already 8 papers per day.
Oh yeah, so this is
exponential. This is exponential growth, and this growth continues already for 5 years at least, as long as far as I am aware of this. So it might be difficult. Well, I'm trying to make it more accessible. So if you scan this QR code, there will be a newsletter there. And so in this newsletter, every week, you will get a selection of new papers or sometimes old papers, selection of sometimes code examples, use cases from industry, if that's possible. Many NDAs are very restrictive in this area. I noticed, like more restrictive even in, I used to work with, classical machine learning a lot with some of the biggest companies in the world, but I feel like when you do causal projects, NDAs are for some reason super restrictive. So we don't always we cannot always talk about real world use cases, but sometimes we can. And whenever I see a good use case or I can share something from my own practice, I do it in the newsletter as well to inspire the community, to show people, we can do this. There's some skepticism sometimes, which is really unfounded regarding this method. So I think that's important. So going back to your original question, that was a very long detour. You can sign to the newsletter, and I hope that that will be helpful for you. On Twitter or X, you can follow the hashtag causal Twitter, epi Twitter, and econ Twitter. There people are also talking about causality. There's a number of people you can follow on LinkedIn and Twitter. What else? There's also a Discord server for my book. So if you want to ask some questions, you can go there. Another great Discord server is for DoWhy, the library, a causal library originally developed by Amit Sharma and Emre Kejiman at Microsoft. Now it's an independent project. There are many people who can help you as well. So I think these resources, newsletter, Twitter, LinkedIn, and Discord servers could be helpful for you.
That sounds great. So I think a lot of questions that are on the chat now are probably going to be asked on those channels. One thing, Alexandre, because I think it's a French name, so I have to go with my French accent. Been asking a very nice question. So it's not you, Alexander, it's Alexandre. Are there any supervised methods in causal discovery? This question is for Jean, actually, because he's working on something for the crunchers. So maybe, Jean, you can touch base on this very briefly right after the last question to Alexander. So maybe, Alexander, if you want to leave, you feel free to leave. The last question I'm going to ask is a question from Xavier. One important aspect of ML is estimating prediction uncertainty. Do causal discovery methods come with techniques to understand how uncertain they are?
Oh, great question. That's a great question. So there are certain ideas, like there's a DESI algorithm from Microsoft that is trying to frame the causal discovery as a Bayesian problem and try to put some Bayesian uncertainty over this. But that's very far away from straightforward, because we don't have a grand truth here. So for instance, if we think about, maybe in the ideal world, we could we could try conformalizing causal discovery, right? But in the real world cases, we don't have any reference distribution. So another way you can think about uncertainty is to look at p-values. If your conditional independence tests are providing this information, you can look at p-values, which is, as we know, it's not a measure of uncertainty really, right? But it can give you some indication of how likely would that data be, or this result be under the null hypothesis. So these are some ideas, but this is largely an unsolved problem, at least as far as I'm concerned. And regarding Alexandre's question, I think you said that Jean has something to say about this.
So about supervised methods.
So I don't know, Jean, what you know. Just like as a quick side note, there are some works, I think, from Francesco Locatello's group as well, that talk about supervised causal discovery. And this is a very interesting topic, by the way. So I'm curious what you will say, Jean.
Well, there is a way to kind of embed the causal graph in a very classical, supervised learning X and Y kind of setup with one huge data set. I want to put together a notebook that I'm going to share by the end of the week for sure, with a concrete example here. But you could embed, for example, instead of looking at the value of the different variable of the system, you could look at, for example, the covariance of the different variable together, and what is the maximum covariance, the minimum covariance, what is the standard deviation of that covariance, what is, all the mutual information, all the descriptive statistics that can happen in one DAG, and then train the model to predict the agency matrix that you showed before with the relationship right together. And you can put that together under quite a classical supervised learning. I don't know how it would perform. Try some random forest on top of that. It's not too bad, but it's still in the context of that specific competition. So I'm not sure if it will perform somewhere else, but I'll put that together.
Right. Guys, thanks for your time. Alexander, I can't thank you enough for having taken the time to be with us today. That was a very, very great time for the community. So hopefully all the questions that we didn't have time to answer to are going to be asked to you on your channels. Guys, also join the newsletter. Very quality content there. Alexander, thanks again. Maybe you want to say something to just call it a quit, or are we good?
Yeah, thank you so much. And I'm super happy to have so many great questions today. I really appreciate all the participants.
Thank you, Alexander. So guys, let's go and join the Alexander social media channels and ask the question there. Let's create engagement, and let's create some trends around causal discovery and causal AI. Thanks everyone for being with us today. This is a recorded session, so you'll find the link on YouTube if you want to go through all the content. Thanks again, everyone, and have a great one. Bye-bye.
Thank you.
Thank
Bye-bye.
you.
Bye.